Hi, welcome to Neuroverse, a podcast hosted by Carolina
and Clara, where we discuss all matters from neuroscience to philosophy and beyond.
Today's episode is on using protein engineering to tackle non-biodegradable materials. And to help with this topic, we are joined by Ryen O'Meara, who's doing a PhD in Professor Francis Arnold's lab, who was a Nobel Laureate in 2018. Ryen carried out his undergrad working on the development of a novel discovery platform for agonist antibodies and is now studying chemical engineering at Caltech and researching how to engineer enzymes to degrade emerging environmental contaminants and merging sustainability and protein engineering. Welcome to the podcast, Ryen.
Thanks, Carolina. It's nice to chat with you guys today.
Cool. So to get started, I want to ask how you got interested in chemical engineering and specifically enzyme-directed evolution, which in my opinion is one of the coolest topics ever.
I realized that chemical engineering allows you, by virtue of having experience with chemistry and biochemistry, to step around and through all of these fields that you might not be a particular expert in, but still make a difference in. So in undergrad, I did research with Dr. Peter Tessier, doing that agonist antibody engineering, and problems in service of human health are really important. I think to some extent, we broadly as a society are not addressing the real issues which result in human health issues, those issues being related to the environment. And I've always been environmentally oriented, and I came to realize that when looking for graduate school opportunities that I could leverage my background in antibody engineering, which is just a more specialized part of a broader protein engineering field, try and use protein engineering to tackle environmental challenges. I wound up here at Caltech with Francis and really on the perfect project to do just that, using directed evolution to degrade siloxanes in service of the environment, frankly.
Yeah, that sounds like such an important cause, and I'm so glad that you were able to combine the chemistry and the engineering to now help with tackle certain sustainability issues, namely in relation to non-biodegradable chemicals. Can you tell us a bit more about these siloxanes and also about your paper on the silicon carbon bond cleavage?
Yeah, so siloxanes are these compounds characterized by the silicon oxygen carbon motif that makes up their backbone, and siloxanes are the building blocks of all silicone polymers. Beyond their use as, the silicones that we're all familiar with, siloxanes are present in personal care products like shampoos and conditioners and deodorants. They're used in sealants and adhesives and lubricants. They're actually also WHO-approved food additives to prevent excessive bubbling, splashing, or foaming when food is added to extremely hot oil. So they're everywhere. And all of these use cases, you can imagine, are open to the environment. They're in your shampoo, you take a shower and you rinse off that shampoo, and your siloxanes along with that water is taken to your local wastewater treatment plant and discharged to the environment. Or it just volatilizes right out of your hair. And there have been studies that have shown that the atmospheric concentration of siloxanes peaks in the morning when, like above an urban area, when people are showering and on their way to work, which is, yeah, pretty funny. But these compounds, they're produced on the megaton scale. So not only are they everywhere and discharged to the environment, they're produced at such scale. And given their physical properties, they're pretty mobile in the environment. They volatilize easily and can transport themselves long ranges through the atmosphere. You can even find them in places that people are not, like the European Arctic, by virtue of that transport. So for us, and the work on the silicon carbon bond cleavage paper was sponsored by Dow Chemical, who is one of, if not the largest global producer of siloxanes. We sought out a means of degrading these compounds.
Could I just
Yeah.
interrupt to clarify one thing? Because this is super cool. I didn't know anything about siloxanes before, but I do think about where my shampoo goes when it goes down the drain every day. No, but I was just wondering, the way you've described it, it's in a lot of man-made products, but is it solely in man-made products or is it ever found naturally?
Yeah, so these are solely anthropogenic compounds,
Okay.
one
And
of
what,
the many.
well, when you say volatiles or
Mhm.
so it reacts with a lot of things, right?
Just
Consequently.
in, yeah, just volatility is, you have it in a liquid solution, and because its boiling point is so low, it's able to volatilize to a gaseous phase. And then once it's in the atmosphere, it goes here and there and everywhere.
And what's the direct impact it has on the environment, other than
Yeah,
the obvious?
no, that's a good question. So right now, they're considered emerging environmental contaminants, and globally, a lot of, there's not a whole lot of consensus on their environmental impacts. The EU is the most concerned with them. Um, One of the siloxanes that we talk about in the paper, this D4 compound, is under consideration to be a persistent organic pollutant. One of the Stockholm Convention POPs. This is a class that includes things like DDT, for example. But siloxanes are known to be environmentally mobile. They're persistent, meaning they take quite a while to degrade in the environment. And even that degradation is not complete degradation, which we can talk about in a bit. And they thus bioaccumulate in organic matter and have been shown to have some reproductive toxicity in rat studies. So they're problematic. The extent of the problem is not yet known, and countries are enacting legislation to take care of them.
That's amazing. I, like Clara, hadn't heard about siloxanes up until I read your paper and clarifying everything with you today. Um, so these would be considered forever chemicals, right? Or not?
Yes, I don't want to say forever chemicals because PFAs are a completely different beast, if you
Okay.
will. But for just ease of understanding, yes,
Okay.
they're somewhat forever.
Sounds good. I mean, your work is tackling the forever aspect, right?
Yes, yeah.
Oh yeah, so could you tell us a bit about what you were going to say about these silicon carbon bond cleavages and how you overcame it?
Yeah, so currently, there's no, or currently, meaning in the past, there is no known enzyme capable of cleaving silicon carbon bonds. And this is important because true degradation of siloxanes requires cleavage of the silicon carbon bonds. So this long polymer is composed of the silicon oxygen backbone, and in the environment, that bond will hydrolyze in water. It'll just be cleaved in half. So what happens is you take these long siloxanes and you slowly break them down into smaller pieces, and you ultimately end up with these small monomers that don't have any more silicon oxygen bonds to break, but to actually degrade them, because if you don't break the silicon carbon bonds, the monomers can just join together again. They can move and continue to cause issues. So breaking the silicon carbon bond is really crucial. And we hypothesized that enzymes might be a really great way to do this because you can chemically cleave silicon carbon bonds, but the means of doing so are not very benign and environmentally friendly. You need things like the acute toxicity of mercury acetate, oxidation in the way upper atmosphere with hydroxyl radicals, things that are just not feasible and applicable to some sort of remediation on a practical scale. But enzymes are great. Enzymes are engineerable, they're benign, and they're environmentally friendly, sustainable catalysts. So we thought that an enzyme might be able to carry out this chemistry, and taking inspiration from the mechanisms of the chemical transformations, which are typically initiated by the oxidation of a methyl group on a siloxane. We tested a variety of oxidative enzymes for that reaction capacity, ultimately finding one that could oxidize the siloxane methyl group, and then through interesting mechanism brings about the SiC bond cleavage.
Could you talk us through a little bit about how you carry out this assay and how you also then direct the evolution of this enzyme for the function that you want? Because we have mentioned enzyme directed evolution in the past, but it's been a few years since I've done biochemistry, and given that you work with Francis Arnold, we'd love to hear your explanation of it.
Yeah, so directed evolution is this really great tool in which you, with no understanding of why something is working, can make enzymes better. You start off with some enzyme that has some small amount of activity towards the reaction you care about, in this case silicon carbon bond cleavage. We found our parent enzyme, if you will. And from there, what we do is we take its gene, perform mutagenesis of it, whether that's just randomly mutating the entire gene or targeting some sites we think are important. And then we come up with this really large library of enzyme variants. They're all transformed into E. coli. We express the proteins, and then we screen them on this reaction that we care about. If you find something that is better than your previous parent, you take that forward into the next round, mutagenizing it, forming a new library, testing that library, and then just repeating this process cyclically until you've improved it to a sufficient point for your purposes, whether that's paper publication or industrial relevance.
Around how long does this process take? Because it sounds like it would take a while to actually then screen the results of this mutated protein. And also, how much do you have to pre-specify parameters in terms of, like, surely you have to optimize it for something very specific and then only look at that specific functional output and see if it's improved or not?
Yeah, so that's a great question because there are two parts to how long it takes. The first is the finding of initial activity. Um, and that's something that in my current work is proving to be very challenging. But sometimes you get lucky and the enzyme you hypothesize will do it based on what it's meaning do the reaction you care about, that you hypothesize based on what it natively does to your chemistry. And there you go. And then you start your cycle of directed evolution. And the key for directed evolution experiments, like you're saying, is throughput, because the things that are better are often comprise a very small fraction of all possible variants. Thus, you need to screen many, many enzymes to find those. So we do this all in 96 well plates, and typically one round of directed evolution comprises looking at anywhere from 8 to 16 plates. So roughly, 800 to 1600 variants. And even that is an infinitesimally small fraction of the total possible diversity of the proteins that we're mutating. And then we use various other high throughput analytical techniques like gas chromatography, liquid chromatography, UV visible absorbance to assess for our activity.
Do you use any computational tools to assess the success of your
Yeah,
reaction?
that's a good question. So typically in the directed evolution cycle, at least traditionally, whenever we present it in a meeting or whatever, we'd show, okay, you mutate, you screen, you find your new improved variant, and you take that forward. All the rest are trashed. The trash can has been replaced with a computer now, because that's all data that can be learned from. And we have dedicated computational people in the lab that are trying to intuit with machine learning the relationship between enzyme sequence and fitness. Fitness meaning the activity you care about. And so far, that's proving a very difficult problem to solve, but most directed evolution work doesn't need machine learning. It's just going to take a lot more screening for you to find what you need. So we're hopefully moving towards a point where, given some reaction you care about, given a protein has initial activity, a model can predict the mutations that you'd need to make to bolster that activity.
Do you use AlphaFold at all to predict the best structure for the enzyme, or do you find that it's not actually that helpful?
Yeah, AlphaFold is definitely really helpful for the ML side, the machine learning side. What's really interesting about enzyme evolution is that you can find mutations that increase activity that are way, way, way far away from the active site of the enzyme where the chemistry is actually happening, clear on the other side of the protein. And in that sense, AlphaFold is not very helpful, because how is this mutation that's so far away increasing my activity? But where it is helpful is when you can use it to come up with a model for the active site, and you say, okay, I dock my substrate in, I just stick it in there, and I see the residues right around it that are interacting with it. And then I could hypothesize, maybe I target one of these residues that coordinates with my substrate. And if it were a different residue, this residue, for example, then I might see an increase in activity because it's bound tighter. And then that's a hypothesis that you can test in the lab and see if it validates.
Right, because there's like so many scales of complexity actually when you think about it, because AlphaFold is addressing protein structure mainly, right? And what you're altering is the genetic sequence, right?
Sequence ultimately does impact structure, like
Yeah,
by
but
change. Yeah.
how predictable is that structure? Like if you knew what sort of, yeah, it makes sense what you said. Like if you knew based on, for example, AlphaFold or some other reason, which site of the protein then you wanted to target, then you could have a more targeted genetic mutation. But as you mentioned, you could also have mutations that you don't necessarily know the outcome on the structure, right?
Yeah,
Yeah.
exactly.
Okay.
It's definitely better for smaller proteins we've come to find in the lab using AlphaFold to predict and somewhat make sense of why a mutation near the active site might be better.
And also, speaking of throughput, I saw that you and your colleagues published a chapter about the development of this new biocatalytic reactor for screening these reactions with the siloxanes. So could you tell us a little bit about that and how you designed it?
Yeah, so siloxanes are a challenging substrate to work with because they're readily volatile, meaning that in your aqueous reaction, they kind of just like to peace out and leave, volatilize to the atmosphere. This is compounded by the fact that they're not water soluble at all. So we needed to find a way to address these challenges. And so we run our aqueous reaction with E. coli cell lysate that has our protein of interest in it. And then we analyze our reactions using gas chromatography. To do that, what we do is we add an organic solvent, ethyl acetate, to extract the products of our reaction from the aqueous phase into the organic phase. And that organic phase is what's injected onto the GC that allows us to visualize and quantify our products. However, the ethyl acetate extracts the plastic of 96 well plates along with our products, and that plastic forms this just intractable gel. It is literally just a gelatinous layer that you cannot separate unless you can centrifuge at very high speeds, which you can't do with a 96 well plate because it's gonna destroy itself. So we need to come up with a way to use 96 well plates because directed evolution hinges on throughput, but without using a plastic plate. And so we played around and found this way that we could rig up a 96 well plate made of individual glass shell vials that you stick with pipette tip wafers into plastic plates and you sandwich another plate on top, and it's an abomination. But it allowed us to perform reactions not in plastic and in glass and escape this gel phase issue and really facilitate the directed evolution that we needed.
That's really cool. I like how you make it sound super DIY. Like the plastic
It
was
really
common in
was.
turning into jelly, so we stuck some
No,
plates and turned them around, and
that is entirely how it was.
That's so fun.
the reality of science.
Exactly. So just going back to the first paper that we talked about on how you develop these enzymes to cleave silicon carbon bonds, what was the result? How successful were you with the design of these enzymes?
Yeah, so this very much is proof of concept that enzymes can now cleave silicon carbon bonds. Their efficacy is not great, full disclosure. But what I think is really important is that we demonstrated you can cleave not only the linear siloxanes, but also the cyclic siloxanes, and the D4 compound, like I mentioned, is the one that has the most regulatory concern around it being assessed as a POP. It's also the one that's produced in the largest quantities per year. So that we could demonstrate activity on this compound in particular was really important. However, to be relevant in a bioremediation context, there would need to be two things two things primarily that are improved. One, just make the enzyme more active. Right now, the enzymes we published, they have about 3% yield of product from starting material. If you want to use an enzyme in any sort of industrial context, for the pharmaceutical industry, for example, they need that number to be at, say, 70-ish%. They can achieve those numbers because they have resources that we don't as an academic lab. They can completely automate their directed evolution, and they're not relying on, grad students and postdocs to do their evolution. And in theory, if we had more time and more resources, we could have continued to turn the crank, if you will, go cycle after cycle and continue to improve these enzymes. But it's outside the scope of this initial paper. So that's the one issue. They're just not good enough at the moment.
Yeah, I mean, it's really exciting that you were able to show that it works. And it would be really exciting to see other companies take this and make it up to 70% yield and actually make an impact, a positive impact on the environment. I also had a follow-up question about the mechanism. So in the paper, you say that you were able to cleave these bonds, and then the result is solenoids and formaldehyde, right? And I just wanted to ask, are these products better for the environment? Are they benign?
Yeah, that is a really good question, because that's the other issue with these enzymes and thinking about biodegradation as a whole. It's that biodegradation necessarily cannot just be concerned with your target compound. You have to also be concerned with the toxicity, persistence, environmental mobility of all the metabolites of that target compound. And so currently, formaldehyde that's released as a byproduct, it's not really too big of an issue. But the silanols that we're making, we and the folks at Dow, frankly, don't know their fate. They're now water soluble, so that would likely restrict them to aqueous environments. They probably wouldn't bioaccumulate as a result, like the parent siloxanes do, but they're not fully degraded. We're only cleaving one silicon carbon bond. To get full degradation, we need to cleave all silicon carbon bonds. That's kind of what my work now is focusing on, which I'll have to just, by virtue of industry secrecy, is kind of all I can say on it.
I also had another question related to this, in that obviously you've highlighted a lot how volatile these siloxanes are, and it's amazing even if the success rate isn't very high at the moment and there's a lot of room for improvement. It's still really cool that there's this opportunity potentially to degrade them. However, if they are so volatile in the environment, how would we even trap them to degrade them in the first
Yeah,
place? If that makes
yeah.
sense.
Yeah, no, my thought on if this, however many years down the line is to be implemented for remediation, the way I see it is that the best case scenario is feeding your wastewater through some bioreactor, say, that has enzyme in it, and allowing the enzyme to work there. You can't really put enzymes in whole microorganisms out into the environment. That is just a really bad idea. You don't want to induce selection pressures on the native microflora. And you certainly don't want to transfer antibiotic resistance markers in the recombinant genome to things elsewhere. So the way I see it, it's really just that. You have a bioreactor with enzyme in it, you feed in your wastewater, and you react it as much as possible. Obviously, you're still going to have the stuff that escapes and volatilizes up into the atmosphere. And how we would capture that, I'm not too sure. And I guess that just kind of goes to speak to the fact that man-made chemicals are being produced at a rate that far outpaces the rate at which they can be rigorously tested for their safety, their longevity, where they end up in the environment. There are too many examples these days of things that did not abide by the precautionary principle. You mentioned PFAs. PFAs are a great example. 3M had known early on that they're they're kind of forever, yet in their internal risk assessments were ignored. What about CFCs? That's another great example of using something and using it at scale, because that's the big problem. They didn't know that they'd react with things in the upper atmosphere and free chlorine radicals that could, destroy the ozone layer. The thing I would like to stress is that while the synthetic chemicals industry has undoubtedly made things that have advanced, humanity's standard of living, the rate at which we're doing so is unsustainable. And I think we need to, one, slow that down, but two, while synthesizing new things, we need to consider their breakdown simultaneously. It cannot be after the fact, after they're discharged to the environment, after they're causing human health concerns. They need to be considered concomitantly.
Such an amazing point to end on, and a good message. And also speaks to the fact that there's a lot of room for improvement and opportunity in researching these compounds and whatever it is you're putting out there, but then also on the other side to break them down. And hopefully there are some pharma companies or someone with a lot of money that wants to go and take these enzymes and make them scalable and actually
Yes.
implement them. That would be really exciting to see. So yeah, policy making and big companies with the big bucks would come in handy to help. But it's really good to see that the fundamental research is being carried out and that these proof of concepts are being validated, and that these enzymes are so malleable and benign and incredible that we can take them and apply it to a lot of our sustainability problems that we currently have.
Yeah, I agree. It's such an important point, and thank you for emphasizing that. And I really appreciate it being explained from your perspective of actually working in this field, because I think it's easy to hear about these environmental problems and think, oh, waste is going to end up in the environment, but to hear this very specific example of this very specific chemical subtype, and what it can actually do just on its own. And as you mentioned, there's so many other materials that can have even worse, more toxic, more long-lasting effects. So it's really nice to hear like the specifics of what sort of damage they could do, but also what can be done to prevent that in terms of considering degradation properties of materials when we make them and then degrading them afterwards. So thank you so much for this episode.
Yeah, that was a great summary, guys.
Thanks for joining us, Ryan. It's been a pleasure.
Yeah, thanks so much.
We hope you enjoyed today's episode. Please feel free to share it with your friends and family. Our Instagram is neuroverse_pod, and our Twitter is also neuroverse_pod. Check out our website for the blog posts and all of the resources we used in today's episode, neuroversepod.com. We'd like to thank the Biochemical Society for supporting Neuroverse, a podcast about science and philosophy. This episode is part of our series to disseminate research done in biochemistry.